record button. The second one is sound. Sound is on. So if you are watching this, if you're watching this on Zoom, you should actually be able to talk today. Let's see. So anyway, we're playing with percentages, and I just want to show you something kind of fun here. So, you know, in the end, we just need to go, I can just make up percentages and so forth. But let's actually try something. Have you ever seen a stereogram? Do you know what that is? It's kind of it was like a thing back in the early 90s. But I want you to stare at the board for a second. And what these are, if you've never seen one before, and if you haven't, you probably won't see this. But just for the fun of it in this environment, let's just come up with a percentage of people who can see this. And so what it looks like when you first glance at it is just a bunch of dots on a piece of paper. Have you seen these? But if you sort of look past it, because you have two eyes that both look at something from two different directions, which is why you are seeing 3D. Like your sense that I'm across the room from you is because you have two eyes. If you only have one, it's much harder to kind of tell what distances are, because effectively you're looking at everything from two locations since you have two eyes, binocular vision. And so this is actually a one-dimensional, or I'm sorry, just a flat two-dimensional picture with a bunch of dots. But if you look through the picture, it's actually, there's a three-dimensional shark in this picture, and this isn't a trick. But can you see it? That's kind of my question. So I'm pulling it up now. So do you agree that just looks like a big wash of nothing? Have you seen these before? If you haven't, you probably won't see this. But again, it just looks like, you know, some blue, someone got loose with the crayons, right? There's nothing special there. What I'm not sure of is you have to have it right in front of you, or can you actually see it from a distance? I'm gonna see if I can get it from here. I've seen these before, so I'm probably a little better at making it happen. Ooh, that's hard. The time at a distance, I can't see it. Maybe that's because of the resolution of the screen. But let's do a different example, because I have kind of a second one. You know, so again, it might be interesting. Maybe this is your final project. You know, something like that, where you just go out and survey your friends and say, you know, can you see the shark that's in that picture? And again, it's not. If I went up there with a pencil and outlined it, that would not help. It's actually 3D. If you get your eyes crossed just right, there's literally a three-dimensional shark that pops out. It's exactly the same thing as what's done in a 3D movie. And you're still watching a flat screen, right? Yet you have the perception that it's 3D. It's the same principle here. But I'm about to show you a woman, same thing, except for this one will work. I'm going to show you a woman now, and I'd like you just to kind of think, how old is this person? Maybe you've seen these before too, but these are kind of interesting. So again, we're just playfully coming up with an example of something that would give us a percent. That's all we're really doing here. So how old is this woman? I'll give you a second to look at it. Rough estimate. How old would you say that woman is? So take it away. Every one of you, I want to know what you think about that. Hannah, how old do you think that woman was? What's that?
I was looking at my phone.
Look again. Esteban on Zoom says 20. Shelly says both young and old. What do you say, Hannah?
Maybe like
20s? What do you say?
20.
You see both? What do you see? Older, 60s? What do you see? Old? What do you see? You've seen it, so you know, yeah, you know what to look at. But again, as a play, I mean, this might be a fun, in a sense, final project. Now, again, does anybody care about this? No. But just to, close the loop. So, I could ask the question, what percent, I could be interested, what percent of people see young and old? And I will say, just as a side note, when I was in college, I was sitting in a 200-person stat class, and there was an aisle down the middle, and the professor had us all kind of put our heads down on the desk, and then one side of the room raised their head up, and then he said, "You're about to see," and he had a picture kind of like this that was dual. So, and I'll show you in a second, but there is a young and an old woman there if you've never seen these before, and I'll show it to you in a second. If you thought she was old, look and see if you can see the young woman. If you thought she was young, look and see if you can see the old one. But what was interesting about the psychology experiment is, I just let you look at it and decide what you wanted. But in this particular one that I was in, the person put a note up and said something about, I'll show you in just a second, both of them so you can see it. But he actually put, and it was a different one, it looked like a man and a woman ballroom dancing in really fancy attire. And it also looked like kind of like a ringmaster with a seal with a ball in its nose. So it's like the same exact picture, two different. But this psychology professor said, "You're about to see a scene at a circus." And then he put the picture up for a couple of seconds, and all of us saw the seal and the trainer, and the seal had a ball in its nose. And then he switched the other side of the room, and he said, "You're about to see a ballroom dancing scene." And then he put the picture up. Everybody saw the ballroom dancing scene. And so, the point of the psychology class was if you're predisposed to think something, then you will. Just now, I just let you kind of think what you wanted. But again, it might be interesting to you, obviously for no real purpose in the real world, but it's just kind of like if you just turn this loose on somebody that's never seen it, then, which one do you see? And so, maybe you get an answer. And so we'll play with that a little bit more in just a second. I'll just make up a percentage. Would you agree that there's not enough of us in this classroom to really have a meaningful percentage? So if I took the time to kind of count, how many people saw the old woman, how many people saw the old, I'm not going to get meaningful data from that, because the N might be 7 for us, right? There's 6 or 7 of us in class. So just to make sure you sort of leave seeing this, if you saw the old woman, then this isn't coming up dark enough. If you saw the old woman, then you saw this is her nose and this is her eye, and here's her mouth and there's her chin. Do you see that now? And she has like a feather in her hat. So if you only saw the old woman, do you see the young? I'm sorry, if you only saw the young woman, do you see the old woman now? If you only saw the old woman, then here's the young woman. This is her face, and this is her chin. There's her eyelash, and there's her nose. This is her ear instead of her eye, and there's kind of the rest of her chin. So it's kind of, it's interesting. These things are kind of playful. There's a bunch of them out there, things of this nature. But again, it's just kind of fun. Anyway, so as an example, let's just kind of play with that for a second to come up with an answer. Now, again, do you agree that this is not something we could ever actually know the answer to? There's not a mathematical way to determine the right answer, and then by comparison to say, wow, that group was really strange. Only 2% of them saw the old woman when the right answer is 12. There's not a right answer to this. So if you wanted to know something about it, you have no choice but to go do a study. And again, as far as the final project goes, that might be kind of fun. You're more than welcome to do something of that nature. I mean, at least if I'm asking people, it would be kind of a fun conversation, if you will, instead of just asking them something like, what's your opinion on politics or whatever. So let's say, given that, again, we are looking at this thing called a confidence interval. Let's say you're interested in that. And so you go ask, I don't know, 132 people. What, maybe, and again, you could predispose them to answer this in a way, and this is kind of a fascinating part of psychology, and also why I told you that previous story. Does it make sense if I said I'm about to show you a picture and I want to know if you see the old woman? In other words, you predispose them to see the old woman by saying that, and then you held it up and let them look at it for a couple seconds, and then, they either say yes or no. So you did that to 132 people. And we'll just say, I don't know, 39 saw the old woman. Can you picture yourself doing a study of that nature? I just want to make sure you have a really clear understanding of how to get a percentage. And so, you know, in the language of our class, that would be X. In other words, that's a variable. Why is it a variable? Because there's an old woman and a young woman, and they might see one or they might see the other. So that's the variable. So you asked 132 people, 39 saw the old woman. And so now you've done a study and you have at least a reasonable answer to the question, what percent of people see the old woman in this picture who've never seen this before? And so, of course, you understand that p hat is found by taking those two numbers and dividing them. You understand how to get a percentage, I hope. And so you get 0.295 for this, and I'm rounding it off. And again, I'm deciding for no good reason that would be rounded to 3 places. I have no good reason for that. And maybe we'll need this later, but as a side note, you understand, and it seemed like we had some formulas that had this, but Q hat is, remember, the percentage left over. In other words, if 29% saw the old woman, then automatically the other ones either saw the young woman or didn't see it or whatever. And so the same thing with the shark. In other words, I could have said, you know, what percent of you see the shark? That would have just taken 20 minutes of class. So I moved on, but it's like, what percent see the shark? 29%. Well, then automatically left over from 100, those don't, right? So in this case, Q, which as you know is 1 minus P, what would that be? 0.705. So I know that automatically. Now, again, what's the big point we've been studying that I want to go deeply into your understanding? This is, if you will, one study. And if you were to go do it again, even if you didn't do it with 132 people, you're not going to likely get 29.5% again. Does that make sense? You're going to get a scattering of different answers. If I said that so much, you want to throw fruit at me and make me move on? I hope so, because if you don't get that, this whole chapter is, this is the hardest section we're in. It's built on a lot of things we've done in the past. And if you don't have a deep understanding of that, this section is going to be really hard. So this is just one study. If I replicated it, I'm not going to get the same answer. However, I did do this with 132 people. And if I did it again, I doubt the second one would be like 78%. Does that make sense? It's probably at least going to be, you know, down in that general vicinity. I guess you might say I wouldn't be surprised. I'm going to erase this, but I wouldn't be surprised if I did a second time and I got like 35%, and I did it a third time and I got, you know, 27%. I mean, that's the kind of answers I'd expect. I mean, again, isn't my 132 person study fairly legitimate? So I would expect the other ones to kind of be down there like it. I would not expect, as I just said out loud a second ago, I would not expect, you know, to have one be 75%. I mean, that just seems like too far away, doesn't it? However, if this person did this with only 4 people, does it make sense? It'd be very likely to get something really weird like that. That is why we said earlier, and I actually don't think this is in your assignment. It's not something I'm going to put on the test. But remember, these samples here, of which I've faked now 4 of them, these samples are normally distributed. Well, the p hats are normally distributed if, remember, NPQ is bigger than 10. In other words, if you check with enough people, because as I said right here, this is really important. If you only check with 4 people, there's a lot of room for crazy to happen, right? Like maybe all 4 people that you check saw the old woman, and therefore now all of a sudden you have 100%. Again, does that feel right to you? I mean, you got to go with a lot of people, or you're just not going to get a very good answer. So they're only going to be normally distributed if kind of like if n is big enough. Well, in our case, n was 132. We got a p hat of 0.295, and we got a q of 0.705. And notice, in a sense, we're about to learn, if this is bigger than 10, then like, whoo, okay, good, I did the study with enough people. But we might learn after all that effort that our study wasn't big enough. And that's kind of what's important about this calculation. So 132, how'd you Garrett? You're wearing that cool shirt again. I like that shirt. 0.295 times 0.705, and I'm sort of on the edge of my seat, and I discover, sweet, that's actually equal to 27. Way over 10. So that means I checked with plenty enough people. Sort of feel like I typed that in wrong. I think it's right. So now I kind of have the opposite feeling. In other words, like, oh, I guess that means I checked with way too many people. You mean I could have been done with my experiment a long time before this and it still would have left the samples normally distributed? Yeah, that's kind of what that means. And so in our case, it's like, okay, cool. I sort of got lucky, right? I mean, I just checked 132 people and it worked. And so awesome. So I have my study, and now can you from yesterday proceed to get a confidence interval? Again, why a confidence interval? What's the concept? Remember, if you did it again, you're not going to get the same answers. You're going to get different answers. And so don't just stop at this and act like it's the right answer. Proceed and tell people what the error in your study is. Is it a 2% error? In other words, the right answer is likely 2%, within 2% of our answer here of roughly 30%. Is our error huge, like 15%? If the error is 15%, I'm going to be not very satisfied with my study. Does that make sense? I mean, if I really want to know the answer to this and I'm like, well, there's an error of 15%, now I feel like, so it can be clear up to 45% and all the way down to 15%. It's like, man, that's terrible. That isn't very, I don't feel like I can count on this. So we're stepping one step past to talk about how confident are we in that 29.5%. As I said yesterday, as a general concept, if you make this 132 a really large number, if we did this with 14,650 people, we'd probably be able to be really confident in our answer. That should feel right to you. I asked a lot of people, so that's cool. So what did we learn yesterday? Let's replicate what we learned. I'm gonna go back here and say CI for confidence interval, so I don't have to write enough. Now, this is all based on you deciding how confident do you want to be. And let's do something a little harder this time. Let's say you want to be, you choose let's say 87% confident. Again, what does that mean? What does 87% confident mean? Given that all the studies a person might do, of which we only did one, we're saying I'm 87% confident that, notice I put P there, not P hat, the real answer to this question around which all of these studies would be. Mine, as I said yesterday, is just one of them. I don't know, is my 29% over here? Is it over here? It's very likely not the right answer. It's probably off a little bit. So that's the problem. See, I don't know where my study landed. I know it's probably off. Is it way off and my study's way down here and actually the right answer is say 40% or something like that? Am I way off and I'm up here and the right answer is actually only 12%? Or is it, kind of pretty close? Maybe the right answer is 30% and I, barely missed it, or it's 32%. But what we're saying is 87% in the middle of this. We're saying our study lands in there somewhere. Does that make sense? We did our study and we want it to land in there. It's kind of like we have an 87% chance of at least being that close to the answer. Now, yesterday I chose some really nice numbers for that, but I think in your assignments, it's not necessarily the case. This time I'm gonna have to push some calculator buttons. So if I'm 87%, there's an 87% chance my study lands in there somewhere. Does it make sense to you that automatically that means there's a 13% chance it won't? Because that's what's left over from 100. So alpha then is 13%. So I just want to introduce kind of one piece of language to you because this comes up in your assignment. Therefore, I didn't say this yesterday because I spent all my time just on the conceptual understanding of it. And again, we have all day to think about this again, which is good. Therefore, the critical value, and yesterday that was half of that. In other words, if we have 13% in those tails, don't we have to split it from the top and the bottom because that 87% is in the middle? So let's see on my calculator, 0.13 divided by 2 is actually 0.065. So that's what the critical value is here, it's 0.065. So that means there's 6.5% in that tail and 6.5% in that tail. So there's kind of a 6.5% chance that I'm way low, that my study was super low. I just asked people that, you know, were jaded in some way or predisposed in some way. There's a 6.5% chance that my study is clear out here. Or there's a 6.5% chance that my study's way up here. And the right answer is actually way lower than 29%. Maybe it's 12 or something like I said before. So notice we kind of had to push calculator buttons for that. So you will see this word, critical value. They'll ask you for it because there's kind of steps to this. Does that make sense? Some of your assignments, instead of having just one question and saying, hey, what's the confidence interval? They're going to say, and that's kind of what I would do on a test. They're going to ask for all the pieces. They're going to ask for all the ingredients. Yesterday, I said it's kind of like a recipe to find the error. Well, this is one of the ingredients right here. You got to know that 0.065 or you're not going to be able to get the Z value. So they'll ask you, what's the critical value? And they want you to say 0.065. So they're kind of giving you credit for all the steps in the process to get that error. So make note of that word, because obviously if I didn't teach you that when you looked at the assignment, you'd think, oh, man, I don't know what's going on. I don't know what they're talking about here. What is it they want me to answer? Okay, so remember the ingredients for this yesterday. To get the error, and I'm going to write a couple of other things down here. You might see this called error. You might see this called margin of error. Again, one of the things that's hard about your assignment is lots of different people made the questions up. And so just like we all choose different words to explain things, you might get a slightly different question. So margin of error, how much is my study off? That's the main point of this section. We said yesterday that's made of two ingredients, the Z-score based on that critical value and the standard deviation of the sample proportions. And then we multiply those two things together. So that's why they're asking for the critical value, because I got to use that to go get the Z-score. So we said yesterday, just to deepen your grasp of this, what do we do to get that Z-score? We say inverse normal. And ideally, we said yesterday, this side over here would be the positive Z-score. Ideally, we want that one. Well, notice the area to the left of that is actually 0.87, but then 0.065. Notice I can't do this in my head. I'm staring at that thinking, I don't trust myself. Even though I'm good at math, I still find myself wanting to add those together on my calculator. I got 0.935. So to get the Z-score that defines the boundary, again, am I inside 87%? Am I in the shaded area or am I outside of it? So I got to have that boundary. I got to know what that Z-score is that represents that location. So I put in inverse normal 0.935. Again, as you did yesterday, interrupt immediately. Ask me questions. You guys online, I might see the chat, but I'm not looking at the screen. So speak up because I think I can hear you. So I'm typing in 0.93501 and I got 1.51. Maybe I'll take it out one more decimal place, 1.514. Notice that came out positive. Just as a side note, honestly, I think this is easier. If you just took the critical value, I'd encourage you to type this in. If you just took the critical value of 0.065 and typed it in there, you're actually going to get this z-score. And it's actually identical to the other one, but what's different about it? You know? Yeah, it's going to come out negative. So honestly, out of laziness, speed, I don't know what to call it, efficiency, I honestly would probably type in 0.065 because I didn't have to do that math to come up with 0.935. I can just type 0.065 and then get negative 1.54, but then just report it as a positive number. So that's kind of cool. It's up to you. Now, would you agree that's not very confident? In other words, remember we said a z-score of 2 was unusual? So we're kind of saying, you know, dude, we're talking about who sees a woman in this double picture. Like, who cares? I don't need to be 99% confident here. So because I'm saying, I really don't need to be that confident, that will actually make my error smaller. Notice that number that I'm going to be multiplying by up here is only 1.5, whereas yesterday it was like 2.05. And so this is going to make the error smaller because you said, I don't really need to be that confident. So however you get to it, we've now got one of our ingredients. So again, your homework assignment could ask you for that 0.065, that critical value. It could ask you separately for that z-score that we just found. And then of course, our second ingredient is that standard deviation up there. So let's figure that out. P hat times Q hat divided by N. Don't forget the square root. What is the answer to that? So I know what P hat is. We said that was 0.295 earlier. And we did figure out Q just for the heck of it, and we've needed it twice now. That's kind of cool. So 0.705, we divide that by 132 or N and take the square root. Because I'm taking the square root, I'm probably going to get some crazy decimal. Again, I would encourage you to push calculator buttons with me. I hope by this point you're not making kind of order of operations mistakes, but whatever you make, I certainly would like to fix it. I got 0.0396. This is a good one to kind of stare at for a second. 0.0396. So if I decided I'm rounding to 3 places, then this 6 would cause that to go up to 10, which would cause that to go up to 4. So even rounded to 3 places, do you agree that that's the right answer to this? Again, on a test, I don't care. Round it however you want. I wouldn't be super happy if you said 0.039 because the 6 tells you that next number should round up. If you called it 0.04 because I didn't say anything about rounding, you just said, I'm going to round to 2 decimal places. Well, then good for you. I don't care. But of course, on MyOpenMath, it's not a machine. It's a machine, not a human. So if it says round to 3 places and you put 0.039, it's going to say you're wrong. Sweet. So that means I've got all my ingredients to find E, to find my error. This is very exciting. So I say, cool, that's 1.514 times 0.04. Again, what does 0.04 mean? It means I did my study and got roughly 29%. And this is saying it's pretty typical to deviate from that by 4%. In other words, this is the first time I realized this, but based on the size of my study, if somebody else did it, it'd be super typical for them to be off of what I got by 4%. And as you know, even 2 of those would be the line for unusual. So they could be as much as 8% off. So if I take that times how confident I want to be, how sure do I want to be it's right? What's at stake here? 1.514 times 0.04. I finally get the answer that I was really interested in, which is 0.0. I'll just call it 0.06, just to keep it simple. So on a test, I could just say, tell me the error. and say nothing else, ask you nothing else, but then just look for the work. You know, do I see all your calculations along the way and so forth? And then I give you partial credit if you screwed one of them up or something of that nature. But I'm very interested that this means something to you. I'm very interested that you get 6% and then you make a decision now. Like, are you happy with your study? I think the answer is 29%, but now you just learned for the first time that there's an 87% chance that your answer is 6% or less away from the actual right answer. The real population proportion of people that see the old woman, again, that nobody will ever know. We're forced to take an educated guess here. So I just want you to understand, lastly, that there's kind of three ways that this could be written down. And this is a little annoying to me. And I, in a sense, only have to show you this because of my open math. If I just said on a test, give me the confidence interval, in a sense, you have three choices. I probably won't say like how I want you to write it. I'm not going to get kind of anal, like do it this way. No, do it the other way. But your assignment will. So I just want to make sure you're kind of clear on this. So, you know, what are your options as far as how you write this down? The first one is the easiest one. This is what I would do out of laziness. And also, I think it makes perfect sense. You say that p hat you sort of say p hat plus or minus error. In other words, what's the confidence interval? What's the options you have for the confidence interval? You say, I think it's 0.295, but it could be plus or minus 6%. As I said, out of laziness, that's the fastest one. And that speaks, right? Like you're done. It just says go up 6%, go down 6%. I'm 87% sure that the right answer to this question is somewhere in that range. So it could be all the way down at 23% or all the way up at 35%. The second way is to actually go ahead and do that. Your book will call that, or your assignment, I think, will call that an inequality. And again, this is what's on your note sheet. An inequality just means, I'm going to pull the note sheet up really fast. That's what I have circled right here. The inequality just means, well, these inequality signs. In other words, put in those less than and greater than signs. Actually do the math. I mean, figure out what the boundaries are. Don't just tell them it's 6% off. Go ahead and add 6%. Go ahead and subtract 6%. And that's exactly what this is saying right here, isn't it? Go ahead and add that 6% to 29% to get the top end of the boundary. Go ahead and subtract it, get the bottom end of the boundary. Tell them what it is. There's an argument for that. I'm very interested that you see that that's kind of like style. Although, you know, this is just a stat class and we're ultimately in here to get your box checked off. You might have an opinion. I think this one's better. I think it makes more sense to me. So the inequality is you actually add. I'm going to go ahead and write out. No, I'm not. Yes, I am. You say that's the top end. And notice I wrote P there. The actual right answer to the question, the actual population proportion we're saying is somewhere, we're 87% sure there's an 87% chance that it's somewhere between these two values. Because as I said, big picture, nobody really cares about your study. If it's wrong, they just want the right answer. So then, of course, you would say, what is that, 0.355? Trying to do this in my head, so I'm not sure I trust myself. Oh, that's the upper end. That's this one. If you subtract it, you get 0.235. There we go. So that's the inequality way of saying it. And again, I think you can see some merit to that. You did the math for them. You made it a little clearer. So now you're saying I'm 87% sure that the actual answer to the question based on my 6% error is somewhere between 23 and 35%. I can't remember for sure if your book actually ever asks for this, but just in case it does, out of laziness, there's another way to write that down. I actually am pretty sure your assignment does ask you for this. Instead of writing it all out like that with the inequality signs, you just put a bracket and write 0.235, put a comma and write 0.355, and then you have to fool around with all the other stuff. It's just sort of a lazier way to write it down. So that's interval notation. And again, that's one of those things that you would have learned in an algebra class had you not just kind of jumped into this class kind of as quickly as you did. So as always, I'm going to post this note sheet after class so you can kind of re-look at that if you want to. I don't care. On a test, write whatever one you want down. I don't care. I would say the advantage of, as I said, the advantage of the second one is that you're adding the P into it, which I think is kind of cool because you're saying the actual right answer to the question is now in the picture. And then you're listing the boundaries. This one is good, but if you showed this to anybody that doesn't understand it, then they might, they might know what it means, and there's no P in it to kind of help you understand like what are those numbers. So in my opinion, the first two both have merit. The last one I don't think does. Last one is just mathematicians' lazy way to write stuff down. It's somewhere in there. So ask you a question. Is it possible that P is 21%? I'm going to erase that because it's going to look weird in the notes, but could P actually be 21%? The answer is, yeah. Remember, we only have an 87% chance of being right, which means we have a 13% chance of being wrong. That means if people went out and did this study and replicated it, 13% of them would come back with a percentage that's in those two tails. Remember, maybe that was me. We only did the study once. Maybe that was me. So when you say a confidence interval, you're basically saying I'm 87% sure that the actual population proportion is somewhere in this range. But that also means there's a 13% chance it's not. So this is still a guess. I mean, did you find that interesting? We're still kind of taking an educated guess at this. So quick pause. How's your brain on that? You feel like you're tracking with it? I mean, I would think you would, best case scenario is, yeah, that I'm tracking, that makes sense. I need to practice it. I certainly need my note sheet in front of me because this is, what, the 20th formula we've looked at in this class. I can see that after 6 months, if I was on the street, I would not be able to do this just like that. I would have to, get it back, look at my notes, practice, that kind of a thing. Okay, a few more examples. And I'm going to basically, I did that one completely, but I'd actually like to give you this time to do this yourself ahead of me. I'll try to shut up long enough to actually give you time to get the answer to this. So we played with cards before. And this is interesting because we actually could get the mathematically correct answer to this question. So that's one of the reasons I'm doing it. But I want you to think, well, we'll think about this in a minute. But what I want to know is, like, I'm going to deal the cards, but this time my question is not, am I going to get a face card? Do you understand there's other questions you could be interested in? Give me some of them. What else could, if I deal a bunch of cards, what else might somebody be interested in? Say again? Colors. So you could say what percent of them are red. Does that make sense? Now you may know the right answer, what that right answer to that question sort of should be in this case, if you know cards. But if I deal out and do a sample proportion, it probably won't be that. What else besides color? What else might you be interested in? Suit. There's 4 suits. And so you could say what percent of these are spades or something like that. What else? All kinds of things. Could be like nines. What percent of these cards are going to be nines? A weirder question. What percent of them are even numbers, that kind of a thing. Or even what percent of them are less than 7? There's all kinds of games that take advantage of this stuff, and people that win at, Reno and Texas Hold'em and those kind of things, or people that kind of understand how to calculate that stuff. Let's go with suits. So what percent of these cards, so I'm just gonna deal a bunch of them out, and I'm not really counting them yet. Actually, I should count them, so I don't have to do it again. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's stop at 17 because it'll make it a weird number. Okay, so I dealt 17 cards. You guys can't see this online. I dealt 17 cards and I'm interested in what percent of them are spades. And I got 1 spade, 2 spades, 3 spades. And I also just noticed there were jokers in the deck. So there's 2 jokers in the deck. So there's actually, no, let's not do that. That's done. Leave it as it is. I got 3 spades. So 3 out of 17. So again, I do a study, I do a sample. My X is the number of spades. A lot of games have spades as trump, and so that would be an interesting question to answer. I decided for no good reason to deal 17 cards. So as you should understand, it could be that I got no spades. It could be that I got 12 spades. I mean, who knows? It's all over the place. If I do it again, I'm not going to get 3 spades. We'll only do this once. So I would like you, and this is the kind of flavor that, a test question would be. I'll say something like that, and then let's produce again, I want to make up a weird number like I did last time, like 87% or something like that. Let's do a 93% confidence interval. That's all I need to tell you. Again, the whole thing is based on error. So you produce a 93% confidence interval. And in our case, we actually got 3 spades. So the question on a test, or even the question on your assignment, should be pretty brief. There's not that much to know. I did my study. I asked 17 people. 3 of them came back with the answer I was interested in. I decided on how confident I want to be. Notice this time I decided this is really important to me, man. This is like gambling in Reno or whatever, so I really want to get it right. It wasn't so important. I went 99%. So I'm going to give you, I don't know, 3-4 minutes to see if you can scratch paper yourself an answer. I'm going to wander. So, because again, this isn't a test yet. If you want to ask me something, just see, you describe it as you do. That also includes you guys online. Again, I think I can hear you if you talk, so I'm wandering around the room, but say something out loud and I'll come back to the screen and talk. Would it help you if now that you have those written down, if I kind of pulled up what I had before, just so you can kind of stare at the process a little more? I don't think you'll be able to see it all, but at least I can make it. Oh, that's pretty good. Again, round however you want. Let's just go there. Basically 93% of the studies that you will do would be from another one. You want to be 93% sure that yours lands, and what you happen to do lands in the middle of the 93%. No, actually, you don't know what the middle is. 93. Well, 93 is more like this percentage. Maybe it's wrong. It's really the area. It's the total area under the normal curve. 90%. See that 87% number right in corner there? We did a 90, at 87% confidence interval last time. Now you're doing it. It's not two separate brackets. Start the bracket. All right, I'm gonna start wading into this. So again, the whole thing hangs on this formula. To get the error, I need the z-score for 93%, and I need PQ over N. So I'm going to figure PQ over N out. So I figure out that P hat is 3/17. And because 17 is kind of a prime number and a weird decimal, I'm going to get a kind of a strange decimal for this. Again, I have no good reason, but I'm going to round that to 0.176. So that means Q hat would be 0.824, 1 minus 0.76. And so over here I say, okay, cool. Then what's 0.176 times 0.824 divided by, would you agree this is a very small sample size? This is not what we did a minute ago. We checked with 132 people. If you only check with 17, you should not be very confident. That's not good. Like, a lot of weird stuff can happen if you only check with 17 people. I'm going to erase this, but as a side note, remember NPQ was supposed to be bigger than 10. So is 17 times 0.176 times 0.824 question mark. Is that bigger than 10? 17 times 0.176 times 0.824. Ooh, not good. It's only 2.5. So you see what I'm saying? Like, this is not a good study. Actually, what this means is, in the real world, these aren't going to be normally distributed. We kind of can't do this, actually, is what it means. So just keep that in the back of your mind. That's an important calculation to know. Actually, I'm going to leave it there because I think we'll readdress that later on. I'll show you something interesting. Stop. So what's the square root of 0.176 times 0.824 divided by 17? It's 0.092 for me. I'm rounding to 3 decimal places. Notice, thanks to the 17, that's a really gigantic standard deviation, right? I got an answer of, or at least I'm sort of saying, I think P hat is actually 17%. And now I just learned, whoa, it's normal to deviate from that by 9%. Wow. Do you understand that the 17 is what's causing this? We only check with 17, so understandable. The Z-score, you've got to picture this. We wanted to be 93%. I'm going to write it as a percent this time. We wanted to be 93% sure that we were right, which automatically means that the leftover is 7%, but we even have to cut that in half, which would be 0.035%, and that's what's actually in those tails. I won't write this down, but remember, your book might ask, your assignment might ask for that, and that thing was called the critical value. So that's kind of what determines how confident you want to be. And so we said, out of laziness, I'll just do it this way this time. If you go in and type in inverse normal, and you just go ahead and use, yeah, go ahead.
Which number is the critical value?
This one. I'll go ahead and write that in the notes. Yeah, it's not the 7%, it's the half of 7%. And the reason they gave that the name is because, you know, that's the one that actually you end up typing into inverse normal. That's the one you need to know. So that's why they chose to give that the name. So again, out of laziness, I'm doing this because I don't have to come back here to get this positive answer and add 3.5% to 93%. In a sense, I'll get a nice positive answer if I put in 0.965 here instead of 0.035. So I will go ahead and write negative, and I'll go ahead and write negative 1.812, but really it's positive 1.812. So then it's these two numbers that I'm multiplying. There's your error. You should be tremendously in the real world bothered by that answer, because this is saying you just did a study and there's like 16, you could be off by 16%. Why did that happen? Because you only checked with 17 people. So this is not a good study. Like you shouldn't even have done this. You should have done NPQ earlier. And I'll show you something in just a second, but you should have checked with more people. This error is huge, both because you wanted to be more confident than last time. Last time it was 87%, and you said this is really important to me, so I need to be really confident. That made the error bigger. And then that 17 made the error bigger. This is so big that, as I said, you really shouldn't have done this. If you leave the negative in this right here, you'll get a negative answer, but you shouldn't. That's why in the end, this is kind of okay, but you're going to get kind of the answer that's down on this side of the picture. In other words, we just got this z-score right here. But really, we want the positive answer. It's actually not wrong, but if you say there's a negative error, it actually still works. You can add and subtract that negative number and you'll still get the same answers. It's just weirder. It's kind of like saying the football team just ran a play and they went -2 yards. Just say they got pushed back 2 yards. Like everybody understands it a little easier if you get rid of the negative sign. So again, maybe I'll just quickly. If you had done it that way, then you would have got the positive answer. So to actually list the confidence interval, as we said, you say plus or minus that error. So that would be 17.6 plus or minus 16.7. Like that's an acceptable answer. But as we said, perhaps a better answer is go ahead and add that. And then you get clear up to 34%. Go ahead and subtract it. You get all the way down to 0.009%. So does that feel worthless? Like, oh, so you got an answer and it's like it could be anywhere from 0 to 34%. It's like, why did you do the study? We have no idea. It's like a huge error. Now, interesting. Do we actually know the right answer to this question? Since it was a deck of cards, can anybody tell us what P actually is? What's the percent of cards that are spades? There's 13 spades out of 52 cards. It's a fourth. P is actually a fourth. In other words, we actually know the right answer to this. This is kind of an interesting side note. So it's 25%. Is that actually in the range there? It is. So again, we have to think of it as, you know, we did a study and got 18%, but it's kind of cool here because we actually know the right answer. So you would never actually do this study because we can mathematically figure it out. We don't have to go ask people like we did for, you know, do you see the old woman or the young woman? You don't have to do a study for that. The answer is 25%. Math tells us that. But it's kind of interesting when we did a study. So it turns out, you know, we got roughly 18%. We missed it by 7%. Well, thanks to this error calculation, does it make sense it kind of actually worked? We said we're 93% sure it's in there somewhere. And it is. 25% fits in there actually easily. That's kind of the idea. Now, let me show you something else. Let me show you this in your note sheet first. So you should be looking at your note sheet. But what I want to highlight is this formula right here. So what I hope you, let me say this and I'll answer your question. What I hope you just learned is like, dude, don't check with 17. Like that was a fail. The error is so big, the study was not that good. So, the second question would then be, well, like, how many should I check with? Because you don't want to just say, oh, 1,500, because that takes a lot of time. It costs a lot of money. So, how many should I check with? Maybe 17 just sort of feels like automatically not right, but is it always 132? So this is going to let us actually come up with an answer to that question. If you want a better error, if you want a smaller error, then how many people do you need to check with? Yeah. I'm sorry, one more time.
I don't think I have one of those mentioned.
Oh, let me, I'll print one for you. I printed them in class and gave them out the other day, but actually I didn't have the one left over. Anybody else not have one? I'll print one. I don't think everybody can see that. Yeah. Now, I won't go into this. I won't go into the details of this, but for somebody that studies algebra, this is the cool part of it. For you, if you look at that formula, you just say, oh, great, thanks. Here's our like 80th formula. My brain is spinning. Totally understandable. For somebody that knows algebra, and again, you shouldn't know it this well, but would you agree that this formula we were using earlier is designed to take these two inputs and then spit out the answer that we wanted, which is air? But let's just count these up in terms of like, variables. There's an E, that's 1. There's a Z, that's 2. P is 3. Q is 4. N is 5. There's actually 5 unknowns there. Could that formula be reworked? And we practiced this a little bit, but this one would be really hard. Could that formula be reworked to be solved for N? And the answer is yeah. With some algebra skill, you could resolve that exact same equation for N, and that's what you get. I won't go into why, because this isn't an algebra class, but that's actually not terrible. If you happen to be interested in that and want to see it after class, I'll show it to you. But that's not really a different formula. From my perspective as like a math nerd, I don't need that second formula because I can make it myself from the first one. So that's just kind of cool. But you don't need to do that. Somebody's already done it for you. Some math nerd already made it. But let's stare at that for a second. So I'm going to snap a picture of that because I don't want to write it down. Notice the squared. Lots of you forgot the squareds on previous questions and assignments and stuff. Didn't want to do that. Would have taken less time just to write it down. So we saw just a little bit earlier that when we kind of did the NPQ thing, we said, is this bigger than 10? We basically found out the answer was no, and kind of a resounding no, because it wasn't even close. Like we didn't get 8.9. That's pretty close to 10. We got 2.5. So this is a question you'll be asked in your assignment. It's actually an excellent question. As I said, 17 should have felt like a bad idea just from the start. If you want to count on the answer you're about to get, don't ask 17 people. There's just too much room for error. One person makes a bigger difference. Well, what should we have done? In other words, how many should we have checked? You see what this formula is designed to do? If I said, well, that didn't work well, I got an error of 17%, that feels like my study's terrible. I don't want an error of 17%. I want a smaller error. Doesn't something like 3% feel like, okay, cool, there's a 3% error in my study. Now at least it feels like I've got something I can count on. Saying the answer is somewhere between 0 and 34%. I mean, come on, that doesn't tell me much. So is there a way to actually calculate what we should have done? Do we have to check with 17 people? No, check with more, but how many more? As I said, if you say 1,500, that's probably going to work, but that might cost you a lot of time and money. Well, look at these ingredients. As I said, it's the same 5 ingredients. There's N, P, Q, Z, and E. That's 5 ingredients. But we're just doing different things. And so what are we doing this time? Well, We knew our value for P, wasn't that 0.176? We knew our value for Q, that was 0.824. We found our Z value of 1.812, was it? I forgot. 1.812. Notice I'm just filling in the numbers. But the interesting thing is what goes there. Now you might say, well, the error. Didn't we just get an error of 0.167 a second ago? But what this is more like this. In other words, suppose you are not happy with your 17% error, and you want rather, how about a 3% error? So it's not like what we should have done in this problem in the real world is not just kind of just randomly pick 17 like I did. We should have done this calculation first, in which case the error is actually something you get to choose. You can actually choose ahead of time. You're not just stuck with 17% of error afterwards and like, oh, that's disappointing. From the very start, you say, I'd like there to be 3% of error. So then I go in here and throw in 3%. Now, again, that's a kind of a big, cool order of operations problem that you hopefully can navigate.
So
You
why
should.
are we taking the percentage of the like sample size we just did rather than like in this case, we know the answer? Are we gonna get the same answer if we would put in the actual percentage?
So we don't know N, like we're recalculating it here because we just sort of
I
saw.
don't know N, but we know the actual percentage of spades in like a deck or whatever.
Right,
So
which,
why are we using like the percentage we got to figure out what number?
nice. In other words, why do we use these when we actually know it's 25? And you're exactly right. Keep in mind, if you said you knew the percent was 25%, then we don't even have to do this experiment. But you're exactly right. I don't know if y'all understand our question, but it's like we're using the wrong answer for P and Q when we actually know the right one. And so if you knew the right one, that would actually be better. Yeah.
I guess I don't understand how we're getting the right number we need from like the percentage we got from a small group.
Yeah, and all I'm saying is, I did this just because I wanted you to see how our study compared to the correct answer. But in the previous one, when I said, you know, how many people see the old woman, we don't know the right answer to that. So we still have no idea whether we were right. Does it make sense in the previous problem? We would have had to use those two numbers because it's the only ones we had. Like you'd actually have to do a study of some kind, even if it was small. Like maybe I went out there and asked 17 people just to get a rough idea, and I got those two percentages, and at least now I could go on and make a better estimate for what N is. So in the real world, you're exactly right. If you know the percentage, 25% is P and 75% is Q, you should stick those in there. Totally, for sure. We'll do another example of this in a minute just to make sure. So can you, and again, I would recommend you do this with me, can you type that in your calculator and get the right answer? Your calculator knows the order of operations, so you can almost just type in what you see there. But again, it's common for people to get all excited typing in all those numbers and forget the exponent. I got N is 529.07. Yeah, so this is somebody, our logic here is to say, wow, the error of 17% here was unacceptably high. Like that makes it feel like my study was terrible. I got a 17% error in my study. So then I said, well, man, that's not going to work. I want a 3% error. The only thing I have control over is how many people do you check with? If you check with more than 17, then maybe you get a small error like that. So then I came down here and said, all right, and in your assignment, that 3% will be given. They'll say, suppose you want a 3% error. So then I redo this with a 3% error, and I got a much smaller error, but then that made me check with a lot more people. And notice a lot more people, 529. So I'd have to have multiple decks, but you could actually do that. Yes. Yeah. And hopefully we'll have time to look at that today, like an example of that. But yeah, that has to be given. In the real world, you could choose it yourself and say, I want a 3% error. But of course, in a book assignment, they're just going to tell you what that number is. So we'll do a few examples of that right now. Now, just as a side note, does it make sense if you chose to round that down, as you probably might initially think? Does that make sense that 3% error would actually be a little higher than 3%? In other words, you checked with slightly less number of people than the math said. I mean, it's got to be a whole number, right? So you can't actually check with 529.07 people. So if you want the error to be 3% or less, this is going to make the error slightly over. I guess that works. Slightly over 3%. Now, is it irrelevant over? Yeah, it is. But I only say this for the sake of the book assignment. You really should round this number up. If you called it 530, then the error would actually be less than 3%. Again, it's not going to be 2.7%. It's going to be 2.99%. It's going to be really close to that. So if the book happens to say you want an error, they won't say you want an error of 3%. They might say something like you want an error of less than 3%. Well, if that's the case, you got to round this up. Anyway, even though it would round off to 529, again, this is kind of splitting hairs. On a test, I would take either one of those answers and say, close enough, who cares? So do you see the logic in this? If I ahead of time, or if I said, okay, I want an error of 3%, then okay, we'll just go do this with more people. So let's start from scratch. Let's do another example from scratch, just like this one. And this pertains to finding n. So let's say you actually do want to go do a study, again, just like your final project, that you have it's an interesting question to you. So what's an example of an interesting question? I'm looking at my notes to see if I had written any down. Tennis. Tennis, you get 2 serves. Usually they hit their first serve really hard, and so if it goes in, they have a really high chance of winning the point. So first serve percentage, and so that's one of the stats you constantly hear if you're watching tennis. And so you're interested in a stat on first serve percent, but there's not a right answer to this question. It's just a particular player. I don't know it's 25%. There's no way to know. What do you have to do? You just have to watch them serve. They served one, it's in. They served one, it's out. You have no choice. But again, the question is, how many people should I check with? Let's say you would like an error of 2%. In other words, you want it to be really good. I'm going to go do a study and I want a really small error of 2%. How many serves should you make that person do so that you could be 2%? There's only a 2% chance, or it's only 2% off of what you actually get. Now, you may remember, it's like, isn't there a lot of ingredients? Like, what's the z-score? What's the, like, we didn't do a study. Does that make sense? We just did a study a second ago with 17 cards, and we actually had answers to those questions, but now we don't. Now we haven't even started yet. My point is, this is a better way to do it. Like, before you do a study, figure out how many people you should check with before you even do it, because we just wasted our time. We dealt 17 cards and we got a terrible answer, and it's like, oh, I was dumb, and then we had to kind of start over. Why not figure it out ahead of time? Well, look at your note sheet. Notice there's a second option here. You have the formula we just looked at, or you have almost the same formula, and this is if you do not have an initial guess, like from either a study you did or some previous study, or maybe you went online and said, what is this person's first serve percentage? And you actually could find an answer to that question. But we don't have one. No one's ever checked. No one's ever looked before. And so notice, in place of P times Q, there's actually just a number in there, like a constant. Just out of curiosity, worst case scenario is if P was 50% and Q was 50%. That makes this N as high as possible. If you take 0.5 times 0.5, you get 0.25. That's where that came from. You don't have to know that, but it's just kind of cool to think about.
So it's always 0.25.
Yeah.
If we don't have a study.
Yeah, if you don't have a previous study. And so notice that's kind of cool because now that's not a variable. It doesn't change from problem to problem to problem. It's a constant. So you might have a problem where they say, oh, there was a previous study and P hat was 3% or something like that, and then you'll have a one. But notice this formula still calls for 2 ingredients. I need E. Hey, we decided that it was 2%, but then I also need a Z-score, and then I'll be able to calculate my answer. So let's go just kind of think about that for a second. Again, I'm going to copy this formula and bring it over. See if I can do this a little faster this time. Didn't copy. I'm just going to write it down. So the important point here is no previous study for P hat. So N is equal to 0.25 times our Z-score divided by our error and squared. That was our formula. So in the problem, we were given an error of 2%. So that's cool. That's easy. But where do I get the Z-score? Well, again, that's something that else that would have to have been given in the problem. So the problem would have to went on to say something like based on and let's say 98% confidence, not confidence interval, but confidence level. Do you agree this person apparently thinks this is really important because they want to be 98% sure they're right? Whoa. If you want to be 98% sure, that's going to add lots more people. Do you agree with that? If you want to be really sure, you got to check with more people. I'm going to do this fast. So what would be the Z-score from a 98% confidence level? Remember the critical value is the leftover percent from 100, 98 leftover would be 2%, and cut in half. So it's half of 2%. So it's 1%. So to get this value, I've either got to say inverse normal of 1% or 99%, either one. Area to the left, this will give me the positive answer. This will give me the negative answer, whichever one. So I'm saying inverse normal of 0.99. And I get a really big Z-score. That's what happens when you want to be 98% sure. I'm going to round to 2 places this time. I got approximately 2.33 for that. So do you see how there would have to be more in the problem? How are you supposed to find the Z-score since the equation is calling for a Z-score here? You can't find that unless you have chosen a confidence level. So the problem wasn't complete as I originally wrote it in blue. So you can say, great, let's go do a study. I only want there to be 2% of error, and I want to be 98% confident. Do you agree those two things go together? 2% error is really low. That's a small error. And you want to be 98% sure you're right. So this must be really important to whoever's doing this study. Do you agree with that? Both of those things. I didn't say a 12% error. I said a tiny error. I didn't say an 80% confidence level. I said I want to be 98% confident. Those two decisions are going to make this N really large. In other words, this person's going to have to serve a lot of servers. So I stick my 2.33 in there. what's the calculator say? 2.25 times 2.33 divided by 0.02. That number squared, I got N is 3393.06. Whoa, you got to check with 3,000 people. Yeah, that's what happens if you say you want to be really confident and you want to have very small error. So if you actually wanted to know what is this person's first serve percentage, this means they're going to have to go serve, 3,400 serves. Now, again, I'm going to add something here that's probably in your assignment. If you said you want an error of 2% or even less, because you're not going to get exactly 2%. Why are you not going to get exactly 2%? Well, we just discovered this person has to serve 3,393.06 serves. Can they serve 0.06 serves? No, it's got to be a whole number. So they can serve 3,393, or they could serve 3,394, but they can't serve the 0.06. If you do 0.06, you're actually going to get a 2% error. If you want it to be less than 2%, like you want your error to be 2% or less, I don't want it over 2%, you have no choice but to round this up. Does the logic of that make sense? Even if it's 0.06, not round off, but round up. As I said, in the real world, who cares? Close enough, right? I want an error of 2%. Do I really care if it's just a hair off either direction? No, I probably don't. But if you really wanted it to be less than 2%, you would actually have to round this number up. Tiny point. Good question. Critical value here is half of that error or that value left over. Since it was 98%, that leaves 2% in the tails, but you got to cut that in half, 0.01. So, my opinion now, relative to time well spent, would be to give you a little time to kind of look at the assignment. I mean, this isn't due till Sunday, so we still have two. What do we have? Today's Wednesday. We have one more day this week. But go into my open math and pull up the 9.1 assignment and start staring at this. And what I'm most interested in is the language. In other words, if you're reading the questions, can you kind of see that maybe they wrote it a little different, but it's kind of like, oh yeah, that's something we discussed today. You need to pore over this, these notes until you get it. Some of you are tracking well enough, studied really hard in 8.1, therefore the things I'm saying to you are going into you. If you didn't study enough, or this is just hard, the things I said are kind of going into you, right? That'd be normal, like some of it's in there. But now you just need some time, I think, and that's kind of what I want to do, is just give you some time to work on my open math. And ideally, you try it, and then it's wrong, and then you say to me, what's wrong with this? I mean, that's where you're going to learn. I need to show you a few things just to kind of get you kicked off to on your way. But really what you need is just kind of practice now. My advice would be like, try to be done with 9.1's assignment tonight. Because what would be really smart is if we started the class tomorrow and I gave you a little time even before I start blabbing to kind of pull up the ones you screwed up tonight, like rather than just kind of burn all your 3 tries or just kind of guess and so forth. Ask me a question in the morning, like, why did I miss this? I had, this answer and I totally thought I understood this. Looking at the note sheet, looking at your notes, and I got it wrong. Guys, whatever I say there is going to go in really deep. Does that make sense? It's going to fix your thinking. So you have the rest of the time. Again, I wouldn't recommend it. Leave if you want to leave. I sort of owe you some time because I went long yesterday. But you got, in a sense, half an hour before the next class comes in. Ask me tons of questions.